Since the beginning, Masonlite have led the neon industry. They have evolved to become world leaders in design, training and production of electrodes and coated tubing. Masonlite are recognized throughout the world as leaders in the manufacture of electrodes and coated tubing, selling to over 60 countries worldwide. Masonlite is totally committed to raising standards in manufacturing and training. The world-famous British School of Neon is truly international, training students from all parts of the globe. This unique school delivers to its students the most advanced training techniques found anywhere around the world. We are continually introducing leading-edge technology to enhance design and produce products that are second to none. Successful production of good quality signs from pre-coated tubing begins with the choice of raw materials. Masonlite coated tubing offers the highest quality available. No matter how tight or complex the curves, you can keep the same uniform color round any contour without cracking or crazing. New colors are constantly developed to cater for the changing demands of diversifying world markets. We have received national awards for the development of processing technology and our heat reclamation systems. Masonlite have been involved in the manufacture and design of pump stands for over 30 years. Our latest turbomolecular system is successfully used throughout the world. For the next 50 minutes, we will be taking you through a compilation of a number of bending and processing techniques, covering pre-coated and colored tubing, the right angle bend, the return bend, the drop bend, forming a curve, the hand torch joint, butt end electroding and processing. Neon sign tube bending is basically combinations and variations of 4 bends and 2 joints, producing the letters and shapes required. The ability to reproduce the bends and joints consistently to achieve good quality is reliant on understanding the correct techniques, which need to be used for bending the glass either in clear, colored, or pre-coated forms. The following demonstration of bending and processing techniques are those used during training by students attending the British School of Neon and form part of the comprehensive courses available. To achieve the best results when working with coated tubing, 4 basic guidelines should be observed. The first is setting the correct flame. The mix of gas and air can vary to some degree, but the width of flame must be sufficient to melt the correct area of glass for any given bend. For example, the width of glass to be melted for a right angle bend should be equivalent to 2 diameters of the tube being bent. Secondly, and related to the width of the melt, is the amount of heating required. Generally, the glass need only be melted sufficiently to enable the correct shape to be formed, with good tube diameter, thickness, and uniform powder coating. Overmelting can lead to phosphor damage, including stretching and thinning of the powder coating. Undermelting will result in the glass folding instead of shaping, leaving a poor quality bend, and in extreme cases of underheating, phosphor may drop off during and after the formation of the bend. Thirdly, the glass must not be allowed to stretch or thin out during melting. This will result in fragile bends, as well as thinning of the phosphor coating around the bent area. Finally, the actual forming of the bends. After heating, simply folding the glass will create poorly formed bends. The glass must be bent by correct movement of the hands to enable the required shaping to take place to achieve good quality bends. Annealing of each bend must be a process added to these guidelines when colored tubing is used. The differences between lead glass and machine-drawn colored glass must be taken into account when it is being bent. Colored glass has no lead content, and as a result is a harder material requiring slightly longer melting times for each type of bend. Best results can be achieved using a more gaseous flame, ideally a flame provided by a single flame cannon burner, allowing more variety of flame types to be used. Colored tubing will develop and retain more stress than lead glass. Poor heating, folded bends, twisting of the glass, severe variations in wall thickness, and contact of the hot glass on cold surfaces will cause stress, which can easily lead to cracks forming and high losses of the raw material during use. Annealing each bend immediately after forming is necessary. This gentle reheating of the glass in a large gaseous flame up to softening point takes the glass to a temperature from which stress can be released and reduced as the worked area of the tube cools evenly. The right angle bend. Roll the tube with the fingers and thumbs of both hands in an even forward movement. Keeping the tube horizontal, melt an area equivalent to 2 tube diameters. Keep both hands rolling the tube at the same speed and do not allow the hands to drift apart. Melt the bend area until it achieves a cherry red heat. When the correct temperature is reached, cease the rotation with the pencil mark uppermost, keeping the tube supported with both hands from underneath. The area of glass directly opposite the mark must now be heated longer. This area, when the tube is bent, will stretch and collapse, and the additional melting will allow this area, the outside radius of the bend, to be blown back to the correct diameter. After melting the bottom area opposite the mark, bring the tube out of the flame to waist height, keeping the tube horizontal. Lean forward and down from the waist and keeping the side in the left hand horizontal and the mark directly below the head shape, the side arm in the right hand in this sequence out, round and up in one easy flowing motion. The correct radius can only be achieved using this movement. When the right side has been shaped around to a vertical position, the right angle is achieved. At this point, lower the head to enable blowing to take place. Blow gently into the tube, only until the collapsed tube diameter is restored. Cease blowing and allow the tube to cool slightly before moving from its held position. The following are examples of the more common mistakes made when forming the right angle bend. The glass has been folded into position and not shaped, leaving a ridge and flat area on the inside radius. The glass has been stretched by pulling before or during the shaping movement. Here, the shape has been achieved, but the outside radius is flat due to underblowing. The opposite effect is overblowing, causing an untidy bend, which may well have a thin glass wall. The fault on this example is only apparent from an end-on view. The glass has been twisted during bending, and if this occurs on several bends on a tube, the finished letter will not be flat. Here, the glass has been allowed to move out of line after the bend has been formed, leaving an uneven shape to the tube. Having completed the right angle bend, we now move on to the return bend. Rolling the tube forwards with all the fingers and thumbs. Move the tube into the flame and begin melting. The area of glass to be melted for the return bend must be equivalent to 3 diameters of the tube being bent. During melting, keep the tube horizontal and the pencil mark central in the flame to achieve equally melted areas either side of the pencil mark. The glass must be melted for much longer than for the right angle bend. When the melted glass glows orange-red, cease rotation, bringing the pencil mark to the top. Keep the tube in the flame and give the area opposite the mark, this will be the outside radius of the bend, additional melting. To aid formation of this bend and make the tube movement easier, as the outside of the bend is undergoing the extra melt, raise both ends of the tube each to an angle of approximately 45 degrees, at the same time ensuring that the radius on the melted area of glass is rounded and equal either side of the pencil mark, and the mark is centrally situated in the radius. It's essential that this is a radius shape and not a V shape. When sufficient extra melting and the pre-shape have been completed, bring the glass towards you out of the flame and down to waist level, ensuring that the 45-degree angle of both side arms is maintained and the mark is directly at the top. Lean forward slightly from the waist, bringing the head in line with and above the central pencil mark. While maintaining the 45-degree angle on the sidearm held stationary in the left hand, shape the right hand until the sidearm is vertical and directly in line with the mouth, ready for blowing. This first shape and the correct area of melt sets up the distance between the two sidearms when the bending is complete, which should ideally be 1 tube diameter. Now bend the left sidearm, and when it's traveled half the distance between the 45-degree angle and parallel to the right sidearm, begin to blow gently into the tube. Keep the left sidearm moving and keep blowing until it's parallel to the right sidearm. The tube diameter, which will collapse due to the stretching during the shaping, will be restored. The most repeated faults experienced forming this bend are folding the glass instead of shaping, leaving a flat area on the inside radius and a pointed tight bend. Stretching one or both sides by pulling before or during shaping. This will also lead to thinning of the glass wall. An obvious fault, underblowing. This effect can also be the result of insufficient melting of the glass. Here, the opposite effect, overblowing, causing an over-diameter shape and the tube wall thinning around the outer radius. On this example, where the glass has been twisted during shaping, the results are evident when the tube is viewed from end on. The drop bend. This bend is used at least once in many letters of the alphabet and is demonstrated as the last bend in this sequence, the center part of a letter E. First produce a return bend with the tube now held flat and the corked end to the left. Mark a line on the tube 70 centimeters from the return bend. This is the position for the right angle bend. Hold the two side arms near the ends and with the mark central in the flame, with the melt area 2 diameters wide, fully rotate the tube back and forth to produce an even melt around the whole circumference of the marked tube, whilst trying to keep the other sidearm out of the flame as much as possible. Keep the tube horizontal throughout the melt process. When the glass is heated to the correct temperature, cease rotation with the mark uppermost and allow the bottom area of glass to melt longer. This will become the outside radius of the right angle bend, and at the same time raise the sidearm in the right hand and create a small radius in the heated area with the mark centrally situated, whilst keeping the left sidearm horizontal. When the outside radius extra melt is complete, raise the tube up to eye level directly in front of the face. Slowly move both hands, shaping away from each other to produce the bend, and blow until tube diameter is restored to the bend. The correctly performed bend will have the pencil mark in the center of the inside radius, correct diameter, and from an end-on view, the right side arm and return bend should be at right angles to each other. The right angle drop bend position is now marked on the left sidearm in line with the mark on the right angle bend just completed. Remove the cork and place it in the other open end. The right-angle bend sidearm is grasped in the left hand, and the sidearm on which the drop bend will be bent is held in the right hand. Note the hand positions on each leg for glass rotation when melting. The glass must be fully rotated back and forth, with the mark position in the flame off-center for this melting operation. Because this is almost two bends performed at the same time, the pencil mark must be offset in the flame. The area of melted glass should be approximately 2.5 tube diameters. When the melting glass glows bright orange, cease rotation and again give the area opposite the pencil mark extra melting. To bring this area into the flame, it is necessary to flip the glass over. When melting is complete, raise the tube to eye level, keeping it horizontal. Allow the heated portion of glass, the right sidearm, to drop down 3/4 of a diameter, then bring this sidearm around in line with the mouth, and at the same time, roll the tube through the fingers clockwise. When both sidearms line up, blow to restore diameter to bend area. Finally, by sight, check alignment of both straight legs and ensure that the drop bend is the correct depth. Because the movement of the glass is more complicated for the drop bend, the faults which occur are more varied and mostly a result of incorrect shaping of the glass. The most common mistakes are folding the glass instead of shaping. This will always leave a crease and uneven glass on the inside radius of the top bend. In this example, the tube has been twisted into position, and the result is an untidy twisted ripple effect, which will have greatly differing tube wall thickness and will retain excessive stress. Here, the rolling motion to produce the second part of the shape has been overdone, leaving the tube angled in too far. This makes the bend look untidy and out of line. The fault on this bend is only apparent from a side view. The glass has been pulled down and forward excessively, leaving a long, stretched, thin-walled bend. The last two examples are the result of either under or overblowing the glass, or too little or too much melting before bending. The next bend in the sequence is forming a curve using the ribbon burner. First, measure the length of curve you need to bend using the blow tube. In this case, the complete right-hand side of a letter C, allowing 15 millimeters extra length at each end of the curve. Using the length you have measured, make sure the ribbon burner flame will be long enough to bend the complete half C. This particular ribbon bend is not tight enough to require blowing, because the outside radius will not collapse. Therefore, a cork will not be needed. Mark the center of the tube length with a chinograph pencil. This center mark will be used to line up with the line denoting the center of the letter C when fitted to the drawing. Next, mark a line 10 millimeters to the left of the first line. This is the mark which must be the end of the melting area, enabling the curve to continue past the center line on the drawing to aid continuity of the curve when the second side is bent. Grasp the tube in both hands out towards the open ends of the length. Roll the tube forwards using all the fingers and thumbs. Melt the tube until it's very soft but not glowing red, keeping it parallel and in line with the burner head. When correct heating is achieved, cease rotation with the mark at the top. Allow the underside of the tube to melt a little longer, and at the same time raise slightly both ends to produce a gentle, even radius. Raise the tube up to eye level out of the flame and shape both hands out and up to produce an even curve, trying to judge the amount of curve by sight to enable easy fitting to the drawing. When the curve is complete, quickly lay it on the bench top to flatten it more quickly to the drawing. Line the center mark on the tube with the center line on the drawing, and while keeping the tube up off the drawing, adjust the curve to fit, followed quickly by flattening again on the bench top. Lift from the bench top quickly and leave to cool down. The second side of the C curve is more difficult to achieve and requires a slightly different method of bending. For the second side, lay the cold curve on the drawing, making sure the first side fits. Remark the center of the glass length, and this time marking the melt mark 10 centimeters to the right of the center mark, so that the melting overlaps into the curve slightly to aid continuity of bending. Place the melt area in the flame with the left hand holding the curve and the right hand holding the straight length. Melt this time by rotating the glass back and forth fully, allowing the glass to heat up the same amount as the first side. Before showing the outside radius extra melt, it's easier to explain how the second side must be shaped to create the correct shaped curve. When the tube is hot, it will bend easier in area 2. Areas 1 and 3 need to be hotter on the outside so they can be bent in a particular order to create the shape. When overall melting is achieved, cease rotation with the first side curve vertical. Melt the underside slightly at the same time, creating a gentle radius by lifting the ends. Move the curve along the flame so that area 3 melts a little more. Then, without disturbing the shape, move the curve back the other way so that area 1 melts a little more. Raise the tube up out of the flame to eye level. Shape first the left side, area 1. Area 2 will then shape on its own. Then shape the right side, area 3. All the time trying to sight to match the amount of curve needed to enable easier fit to the drawing. When the curve is complete, quickly lay it on the bench top to flatten it. Turn it over so that the second bend side corresponds to the left side of the C drawing. Move the tube quickly to the drawing, holding it above the drawing to stop it burning. Fit the cold first bend exactly to the right side of the drawing and adjust the still soft left side to achieve a good overall fit. Lastly, lay the curve on the bench top to flatten completely. Lift from the bench quickly and leave to cool down. Another method of producing a curve popular in many countries is by slow bending. This technique is ideal for both colored and soda lime glass and is demonstrated here using clear tubing. Mark the center of the tube length with a chinograph pencil. This mark must be lined up with the center line on the drawing every time the tube is fitted to the pattern. Set up a large, wide, soft flame with a blue color base, but with a yellow top area. In slow bending, the glass must only be melted to just soften it. If it's melted too much, the correct shape cannot be achieved. We will now bend the curve to fit the right side curve of a letter C. Place the glass in the flame 2/3 of the way up its overall height. For the first bend, roll the glass forwards with all the fingers and thumbs of both hands, with the hand positions far enough towards each end of the tube to ensure good balance. When the heated area softens, stop rotation. Raise the tube to head height and move the right sidearm upwards to create a small bend at the mark position. With the pencil, mark the tube to the right of the first bend, approximately 10 to 12 millimeters along. Return the glass to the flame, and now with the back and forth rotation, soften the area where the mark has been placed. Again, when the glass softens, remove the tube from the flame and raise the tube to head height. Move the right sidearm up to produce a second slight bend at the mark point. Turn the tube at eye height, giving a view down the length of the tube, and check or correct alignment to keep the bend section flat. Now, lay the tube over the drawing with the first mark on the center line, without making contact, and check the fit of the curve being produced against the curve of the letter C drawing. The bent area should follow exactly the inside line of the drawing, and the straight unbent length should leave the drawing at a tangent. The position of the next bend is now marked with the pencil at the point exactly where the inside edge of the tube departs from the inside line of the drawing. Continue this bending, checking and marking process until the first side of the letter C is complete. If the tube has been fitted to the drawing and marked and bent correctly, an exact fitting gentle curve will be achieved, with all the marks equidistant from each other. If the alignment and straightening after each melt has been performed correctly, the half curve will be flat when laid on the bench. The second side of the letter can now be bent, using the same process, always checking that the first side is fitted to the drawing before checking or marking the next bend on the second side. From the bending exercises, we now move on to the hand torch joint or splice. Place the cutout block on the bench top. Set up the cork tube on the left-hand side and weight down the tube with the blow tube attached on the right-hand side. Set up a medium-sized soft flame on the hand torch and carefully preheat the two open ends to be joined to prevent thermal shock cracks. Grasp the tube on the left side and move it towards the other open end until the two open ends are 1 millimeter apart. Adjust the flame on the hand torch down to a wide, fairly strong flame. Keeping the flame at right angles to the tubes, begin melting the two open ends, rotating the hand torch at speed back and forth to effect equal heating right around the two open ends. When the two open ends melt to a dull red heat, remove the flame. Touch gently together the two open ends. Give one gentle blow and at the same time pull out slightly the left-hand tube. This blow and pull action will remove some of the ridges and folds pushed into the joint by the initial contact. Adjust the hand torch down to a small, sharp, bright blue flame. Begin melting, pointing the flame at the joint line and fully rotating the hand torch back and forth at speed to again effect full melting right around the joint until the heated area glows bright red. Because the flame is rotating and not the tube, gravity will have an effect on the melting glass, and the hot glass on the underside of the joint will sag down, and the hot glass at the top of the joint will collapse. If this is not counteracted with an extra melt before blowing into the tube to restore diameter at the melt point, an uneven joint will result. At the end of the first full melt, when the glass at the joint area reaches a bright red heat, cease flame rotation. Bring the flame to play on the top of the melt area and heat this collapsed area slightly longer without increasing the depth of the collapsed glass. Remove the flame and blow gently into the blow tube until the tube diameter at the melting point is restored evenly around the tube. After this melt and blow operation, many of the ridges and folds in the joint will have been melted away. At the end of this repeat melt and blow, all of the ridges and folds should have been melted away. If this is not the case, a further melt and blow will be necessary. The final melting operation can now be performed to smooth out the surface of the melted area and the correct diameter and glass thickness. Again, melt fully around the joint area with the same small sharp flame until a bright red heat is achieved. At this point, and just prior to giving the top of the heated area its extra melt, very slightly push the tube on the left towards the tube on the right to thicken the glass in the melt area. Bring the flame to bear on the top of the heated area to achieve the extra melt. Remove the flame and blow gently into the blow tube until the heated area slightly exceeds diameter. Pull back gently on the left-hand tube until tube diameter is restored and the correct wall thickness is achieved. Finally, adjust the hand torch to a large, soft flame and anneal the whole of the heated area and glass up to 15 millimeters either side of it, right around the tube. Most of the faults associated with joints or splices are a result of the melting and blowing of the glass. The first action of touching the two pieces together is the foundation of a good joint. Here, the initial contact was too firm. The glass has rippled up into ridges and folds, which require more melting than normal to remove. Evenly melting right around the joint has not been achieved here, and will leave a bulge at the point receiving most heat. On this finished joint, the uneven glass is the result of over-melting or melting too many times. This is a joint where the melting has been too little or too few times. It has good wall thickness and is even across the joint, but still has ridges and folds, which will contain stress. Here, the joint has been melted correctly, but the final action of blowing and pulling apart was excessive. Finally, this joint has a thin tube wall and is under diameter, caused by underblowing before the final pulling apart. The last operation of bending neon tubes is electroding. The following method highlights the technique used throughout Europe and differs substantially from the style practiced in the United States. The result of both methods shows that the European technique guarantees no possibility of phosphor thinning at the tube ends. This generally happens using the other technique if the glass is stretched and thinned excessively during the forming of the double back bends prior to electroding. It is also apparent that the butt end shape allows the sign fixer to install sections of neon tubing very close together, giving the appearance of continuous line. Mark the position of the electrode with the chinograph pencil. Set up the same small sharp flame as used for the hand torch joints. Keeping the flame at a right angle to the tube, begin to melt slightly to the right of the first mark. As this area melts, keeping the flame rotating in the same position, pull off the excess glass with the tweezers until it separates from the main tube and leaves a closed end. The now closed end will be slightly pointed and still have some small excess of glass which must be removed. Again, using the small flame, melt the closed end by pointing the flame directly at the closed end until glass is red hot. Remove the flame, blow gently into the tube via the blow tube. The hot end will bubble slightly. Grip this with the tweezers and pull outwards until the glass solidifies. Now melt on the shoulder of the closed end, rotating the flame at speed, and pull gently with the tweezers until the excess glass is removed. To shape the butt end again, point the flame directly at the closed end, allowing the glass to melt back slightly. Remove the flame and blow the glass out until it flattens at the end against the flat surface of the tweezers, forming a neat, semi-rounded closed end to the tube with the correct wall thickness. Anneal thoroughly. To form the electrode joint hole, again using the small sharp flame, point the flame directly down to melt between the butt end and the second pencil mark. Allow the glass to melt down slightly, remove the flame, and blow into the tube to produce a 15 mm diameter bubble. Increase the gas content of the flame making it bigger and softer. Melt the glass of the bubble halfway down its height. Remove the flame and blow the glass up into another bubble. Melt down the bubble again halfway down. Remove the flame and blow this time to form a large, thin bubble. Break this open with the tweezers, melt back the rough edges of the hole to leave a 15mm diameter hole with a flat, clean-edged shoulder. Anneal the butt end and hole and surrounding glass with a large soft flame. Having produced the butt end and hole with a soft flame, preheat the open end of the electrode glass. Reduce the gas content of the flame to produce a wide, fairly strong flame. First, melt the open end of the electrode glass sufficiently. Bring it into position close to and directly over the electrode hole. Melt evenly both parts and complete rotations of the flame. When both parts are correctly molten, remove the flame, touch gently the open end of the electrode to the edges of the hole, give a slight blow, and pull upwards gently. This blow and pull will thin out some of the ridges and folds formed by the initial contact. Quickly set up the same small, sharp flame used previously. Keeping the flame at right angles to the electrode, melt across the joint line with complete rotations. Hold the electrode steady, not allowing any upward or downward movement during this melt. When the glass is showing a bright red to orange heat, remove the flame. During melting, the diameter of the electrode glass will reduce. Blow gently until the correct diameter is restored. Do not overblow, as this will thin the electrode tube wall thickness. Heat up the glass again and repeat the melt and blow. At the end of this second melt, if successful, the joint will be clean and clear, with no ridges or folds visible. If this is not the case, a further melt and blow will be necessary. Remember, do not allow the electrode to move up or down during these melts. The final melt is performed the same as the previous ones. The blowing of the tube is slightly different. For this operation, when the tube is red hot, remove the flame and blow into the tube until it is just over diameter. Now, pull the electrode upwards gently until the correct tube diameter and wall thickness is achieved. Finally, anneal the completed heated area thoroughly. Having produced a good right-angle electrode joint and thoroughly annealed the glass, the return bend can now be made. The wall thickness of the electrode at the end of the joining operation must be correct prior to melting and bending the return. Set up a fairly strong flame wide enough to melt a 2-diameter area of the electrode glass. Angle the flame down slightly and melt with complete rotations around the electrode from the joint line up. As with the electrode joint, do not allow the electrode to move up or down during melting. When the area being melted reaches a bright red heat, cease rotating the flame and direct it at the area which will become the outside radius of the bend, and melt this area longer. This outer radius will stretch and collapse as the bend is formed, and must be affected more by the blowing action to maintain the diameter of the tube on the finished bend. At this point, remove the flame, shape the glass, performing an up and over movement with the hand to produce the bend. When the movement reaches the halfway point, begin to blow. Continue the blowing and bending until the electrode is parallel to the tube and the correct glass diameter of the bent area is achieved. The distance between the electrode and the tube should be 1 tube diameter, and the electrode should be parallel to the tube and directly in line when viewed from above. If this is not correct, alignment can be adjusted during annealing. Each tube manufactured has 2 electrodes fitted. The first one of these must have the pumping stem fitted. Having joined the electrode to the tube in either the right angle or return position, the pump stem must now be added while the glass is still hot. Using the same 3-melt method used in producing the electrode hole, but with a smaller flame, blow a 6 mm diameter hole in the desired position, in this case the outside radius of the return bend, making sure the hole has a shoulder of glass around it to make contact with the pump stem easier. When the hole has been produced, anneal again the heated area. Using the same small sharp flame, begin by melting the open end of the pump stem. The stem is usually a 15 cm length of 6 mm diameter tubing. Bring the pump stem into line with the hole and, keeping the flame at right angles to the pump stem, melt both parts using a full rotation of the flame. When both parts melt to a dull red heat, remove the flame. Touch the stem to the hole, blow slightly and pull back slightly. Now, melt the stem glass just behind the joint line, making sure there is no push or pull motion by the hand holding the stem. Again, keep the angle of the flame correct and complete full rotation with the flame to produce some heat right around the joint area. When the glass is red hot and has reduced in diameter, remove the flame and blow gently to restore the correct diameter, making sure not to pull the stem out with the support hand. Repeat this method until a good, clean, clear, ridge-free joint is achieved. The last melt and operation will produce the required shape to the pump stem joint. Melt the same area in the same way, allowing the stem glass wall to thicken slightly. When the glass is melted to a bright red heat, remove the flame, allow the glass to cool a little, then pull back gently to produce a restricted shape with the correct wall thickness, and bend the stem downward slightly, leaving it in line with the electrode. Finally, thoroughly anneal the pump stem joint, the electrode return bend, and the area around the electrode joint with a large, soft annealing flame. The final stage in the production of neon tubes is the processing. Although it is easier to perform than the bending, its importance to the quality of the finished tubes is paramount. Light output, color, brightness, and the length of life of tubes will all be affected, sometimes dramatically, by incorrect processing. The same results would also be apparent if the processing were carried out on poorly maintained or inefficient equipment. The following procedures are those recommended for processing with Masonlite A activation electrodes, and the current settings used are those for the 30 milliamp types and should be adjusted as shown on the chart for other sizes. Method 1. Open stopcock processing. Before joining the tubes to the system, the mercury is inserted into a reservoir on the pumping tubulations. Masonlite recommend 400 milligrams or 3 to 4 millimeter diameter ball of mercury for each tube. Excessive mercury can, if being moved around the inside of the tube without care, remove phosphor coating from bends and over a period of time condense heavily on cold areas of the tube, causing severe staining, especially on bends. Too little can lead to mercury starvation, as it migrates from one area of the tube to another and leads to tubes dulling at one end. Seal the tubes onto the glass manifold. Try wherever possible to process 2 tubes at a time to increase output. Tubes pumped together must be the same diameter, the same rare gas filling, and have approximately the same tube footage. After sealing on, close the air admittance stopcock. Connect the electrodes to the high-tension leads and insert bombarding mica into areas where tubing runs close together as a precaution against arcing through. Next, connect a reliable temperature indicator at the center of one of the tubes. A good quality temperature gauge and thermocouple is recommended for accurate measurement. A piece of paper is a popular way of judging tube temperature, but is notoriously inconsistent, as different types of paper will give different indications. The bombarding stage of processing can now commence. Open the main stopcock slowly to allow the pumps to begin evacuating the tubes. When the tube pressure falls to 6 torr, registered here on the capsule dial gauge, switch on the current. Allow the pressure to continue falling, and at around 2 torr, the tubes will strike up. At this point, close the main stopcock. If the pressure is allowed to continue falling, a flashback down the glass manifold can occur, leading to possible equipment damage. Increase the current to 150 milliamps. As the tubes begin to heat up, the pressure will increase slightly due to vaporization of moisture. By briskly opening and closing the main stopcock, the pressure can be reduced to 2 torr. Allow the bombardment to continue, increasing the current slightly if necessary to effect gradual heating of the tubes until the temperature reaches between 150 and 170 degrees centigrade. At this point, increase the current to 400 milliamps. Open fully the main stopcock. Allow bombardment to continue until all the electrode shells are glowing bright orange-red along their whole length, an approximate shell temperature of 900 degrees centigrade. The tube temperature must reach 250 degrees centigrade. Switch off the current. Allow the tubes to evacuate to between 10 and 20 microns while the tube temperature falls to approximately 100 degrees centigrade. The second stage of the process is the helium rinse. Open fully the first helium bottle stopcock to evacuate any impure gas in the sidearm between the stopcocks. Once the vacuum has reached between 10 and 20 microns, close the main stopcock. After closing the helium stopcock, introduce helium gas into the tubes via alternate use of the stopcocks until a pressure of 4 torrs registers on the capsule dial gauge. Switch on the current and increase to 500 milliamps. Allow the tubes to burn for 1 minute. Helium rinsing serves 2 purposes. Firstly, any residual gases or contamination left in the tubes will be diluted by the helium. Secondly, if the gas color remains a consistent straw yellow around the complete tubes, this indicates clean, well-bombarded tubes. If the gas discharge color deteriorates due to contamination, a second bombardment can be performed using the helium gas in the tubes. To do this, increase the current to between 700 and 900 milliamps and effect full heating of the tubes once more to 250 degrees centigrade. Then repeat the rinsing process to assess the results. At the end of the 1 minute running time, if the gas color is satisfactory, switch off the current. Open fully the main stopcock and allow the tubes to cool and evacuate. Once the tubes have fully evacuated to 1 micron or below, and the tube temperature has fallen below 50 degrees centigrade, the final stage of processing the rare gas filling can take place. Fully open the first stopcock of the rare gas to be introduced to evacuate any contaminated gas in the sidearm between the stopcocks. When this gas has been pumped away and a vacuum reading of 1 micron or better has been re-established, close the small stopcock. Close the main stopcock. Introduce, by alternate use of the small stopcocks, the required amount of rare gas. In this case, the 15mm diameter tubes are filled with 8 torr of blue gas, registered on the capsule dial gauge. Switch on the current set at minimum to visually check the finished tube. As this chart demonstrates, gas filling pressures vary according to tube diameter and type of gas. Reliable, consistent gas filling pressures are as important as any other part of the processing of tubes and needs to be achieved as accurately as possible with every filling operation. Once the visual check is completed, switch off the current. Remove the mica and disconnect the high-tension cables. Seal off the tubes from the glass manifold. Introduce the mercury into the first electrode. Then, carefully tip some of the mercury around the tube to rest in the other electrode. Seal off the pumping stems and set the tubes up to age in on the appropriate transformer. Method 2. Closed stopcock processing. The initial bombardment stage of processing uses a slightly different procedure than Method 1. As can be seen from this chart, more current settings are used at various stages through bombardment. The main stopcock is used much more frequently, but is only kept fully open for a very short period towards the end of bombarding. After the tubes have struck up, close the main stopcock and set the current at 150 milliamps. The tube pressure will be approximately 2 torr. Allow the bombardment to continue. The tube pressure will increase due to gases released under heating. When this increase in pressure takes place, open and then close quickly the main stopcock to evacuate some of the released gases to bring the tube pressure back to 2 torr. At the point when the tube temperature has reached between 150 and 170 degrees centigrade, increase the current to 250 milliamps. As the bombarding continues, use the open-close stopcock movement to maintain 2 torr pressure. The electrode shells will now begin to glow dull red. At a temperature of between 200 and 220 degrees centigrade, increase the current to 400 milliamps. As bombardment continues, the now rapidly heating electrode shells will be releasing gases which must be pumped away continuously using the open-close stopcock movement to maintain 2 torr pressure. When all the electrode shells have achieved a bright orange-red heat along their whole length and the tube temperature reaches 250 degrees centigrade, the main valve should be fully opened and left open as the bombardment continues for 5 to 7 seconds. Switch off the current and allow the tubes to evacuate fully. Continue the process exactly the same as for the open stopcock method. Helium rinse, gas fill, seal off, and age. Technical sheets covering both processing methods and the helium rinse are available on request from Masonlite.
Here at Masonlite and the British School of Neon, students attending our courses will be with us for a minimum of 20 weeks. This video is only an introduction to tube bending and processing techniques. It is not intended to teach you tube bending in 60 minutes. We also have a wealth of scientific and technical expertise available to you.